1A, the goal is to find the voltage output of the circuit, and based on what is appeared right here, it looks like a clamp circuit with a capacitor and a diode with a negative clamp circuit. So it's gonna shift the whole graph up, and if we look at the graph for V in, the capacitor is fully charged at 2 milliseconds, and at that point the V input is gonna be equal minus 6.7, and if we do some basic calculation, we know that minus 6.7 minus minus 0.7 the voltage output of the diode, so it means the whole graph gonna shift up by 6. So this is how the output of the V out look like. So the whole thing gonna shift up. So the original is start from minus 6.7 to 4, so the whole thing shift up by 6. So we're gonna get the graph look like this. But 5.5 is gonna go from 10 go down to minus 6, minus 0.7, and go back up again. So for question B, the switch is closed at 9.5, so at that point the current start flow to this state 2, and the question is to find the voltage output 2 right here. So we know that this is the state 2, the graph, the circuit. This circuit is the integrator circuit with negative feedback. So in order to find V out, we can use the formula right here. So V output 2 equal minus 1 over RC, integral from 0 to T. It's just the time of the V input, tau d tau. So for example, of the calculation from T equal 9.5 to 10 millisecond, we can have V output at 10 gonna be V output at 9.5, which is equal to 0, because at that point the switch is closed and there's no output, equal minus 1 over 100 millisecond, integral from 9.5 to 10, and the V input at that moment is 10 volt d tau, and it's gonna be equal 1 over 100 times 10, and the difference between the two is 0.5 millisecond. So millisecond gonna cancel out, and we're gonna get 5 over 100, which is equal minus 0.05 volt, which is equal minus 50 millivolt. And for the next calculation, it's gonna for T from 10 millisecond to 11 millisecond. So using the same formula, V output at 11 minus V output at 10 gonna be equal minus 1 over 100 millisecond, integral from 10 to 11, and the V input at that moment is minus 0.7 d tau. So we know that the V output we just find right here gonna be minus 50 millivolt. So we do the calculation. This is gonna be V output 2 at 11 minus 50, which is plus 50, equal 0.7, and the difference between these is 1 millisecond. The milliseconds can cancel out, it's gonna be, and then after do some calculation, it's gonna come with the result of minus 43 millivolt. And we do the same calculation for T from 11 to 12, 12 to 13, 13 to 13.5, and here's the answer that I get. And we can put it on the graph, and the graph looks something like this. At 9 it's gonna equal 0, and at 10 is gonna equal minus 50, and then it's go up, and then it's go down and up and down. The reason why the graph go down is because of the voltage output that we measure right here, which is plus minus. And if we want to shift the graph up, we can just reverse the side terminal of the voltage meter. And for question C, the goal is to find how many poles that it takes for the circuit to reach 10 volt. So I can think this I think the problem can be solved this way. So 10 volt can be equal the number of poles times the difference within one pole, and we know that within one pole the circuit go from minus 0.7 to 10, so the difference gonna be equal 9.3, and we know that the time constant gonna be equal 100. So plug everything in this formula, we get x number of poles equal 10 divided by delta is equal 10 over 10 minus 0.7 divided by 1 over 100, and I got 107 pole. So it takes 107 poles for the circuit to reach 10 volt. And for question D, so the question is the effective of R1 to V01. So the concept is just the same as the peak detector on lecture note. So if R1 is not large enough, the current let's go back to the circuit. So when this one is closed, and if R1 is not large enough, the voltage gonna dissipate on this R1's resistor, and it's gonna affect the whole circuit. So in order to avoid the load effect, I want it to be very large compared to the state 1 circuit to prevent the loading effect. And for problem 2, here is the circuit, and the question needs to find the voltage output. So we have the 15 volt input, the current source, and we know that current source can absorb some voltage as well. So and we know that the V input right here, it has amplitude of 5, so it's gonna go from -5 to 5. So when V in equal 0 to 0.7, so the diode gonna D1 gonna be off, and the voltage output is always equal the voltage across this resistor, and at the voltage at A, and we know that the current is gonna go through this branch, and the voltage across the resistor is gonna be equal 1 milliamp times 1 kilo ohm is equal 1 volt, and the V output is 1 volt plus VA. So when the first diode is off, the voltage across this diode is 0.7. So if we add it up, it's gonna equal 1.7 volt. And when the V in is equal 0.7 to 5, the first diode is still off. It's in reverse. It's gonna be off. So V out is still equal 1.7, and when V in is equal 0 to minus 0.7, this one is the voltage across this is not strong enough, so it's still off. So the voltage output is still equal 1.7. And then when Vi is go beyond minus 0.7 to -5, so at that point we know that the VA gonna be the voltage at A VA gonna be equal V in subtract the voltage across the diode. It's gonna be -5 minus 0.7, so it's gonna go -4.3. So VA is equal -4.3, and we know that V out is equal 1 volt plus VA, so V out gonna be